A couple more examples using A cross B, the Cartesian product. We could simply say that the ordered pair 1, 2 is an element of the natural numbers crossed with the natural numbers. 1 is an element of this, 2 is an element of that. I also could have said integer cross integer, z cross z, or r cross r for the real numbers as well. And another one would be negative pi, comma 1/2 is an element of r cross r. So whether you realize it or not, this is something you're probably very familiar with. The xy plane, the Cartesian plane, is r cross r. Sometimes this is written r squared. Okay, so for Cartesian product, let's say that our set capital X consists of lowercase l, m, and n. And let's say that our set capital Y consists of 2, 3. Well, that means that we've got X crossed with Y. And whenever you do this on a set that has a finite number of elements, both of these do, you can count the number of elements in this set, which is 3, and the number of elements in this set, which is 2, and you're going to get 3 times 2, or 6 ordered pairs. So order doesn't matter, but I think I'm going to take L and match it with the 2 and the 3 both. And then I'll take M and match it with both of the 2 and the 3. And then finally I'll match N with 2 and N with 3. So that is the Cartesian product of the two sets X and Y. I think I'll squeeze in one more definition down here at the bottom. Probably a definition that we all know, but maybe you've not seen it exactly like this. A function f. So we're defining a function. And I think for this, I'm going to use a capital F. I usually use lowercase letters, but a function f is a relation with a certain condition. Where the following hold true. X, y is an element of the function, that ordered pair xy, and xz, also being in that function, requires that y and z be the same number. So y is equal to z. And I'm going to continue a little bit more. Oops, this means should be an arrow. Implies. So for example, in a previous example, I don't remember what it was exactly, but I had something like an ordered pair with 1, 2 and maybe 1, pi, something like that. You can't have you can think of a function as mapping the first element into the second element. Well, a function is not allowed to map one element, like x, into both y and into z. So if you have this in a function and that in the function, since x is the first element in both, y and z must be the same. Okay, I'm going to define the domain and the range or image of a function. See if I can squeeze it down here. The domain, which I'm going to abbreviate usually like with DOM of f, domain, is equal to the set of all x elements such that xy is in the function for some y. So x, y is an element of f for some y in, yeah, I'll just put for some y. Okay, so you can look at every single ordered pair in the function, take all of the x elements, the first component in the ordered pair, that collection, that set, makes the domain of f. And again, I'll usually abbreviate it like that. Then the second one is going to be the image of f. And I'll frequently write that with just im of f. And I could put parentheses around the f in both cases if I wanted to. Well, you might suspect what the image is. It's the set of all y such that x comma y is in the function f for some x. So if you take the set of all ordered pairs of the function, the second element of all of the ordered pairs, if you put them in a set, that gives you the image of the function f.